Okay, welcome back to the session of the differential equation. Today, I like to discuss with you the exact differential equation. Actually, exact differential equation is a differential equation which is directly derived from the primitive. What is actually primitive means is the solution of a differential equation. See, consider the function x square plus y square is equal to c square is a solution of a differential equation. We can directly differentiate this function, differentiate both sides. By differentiating this differential equation, we will have 2x derivative of x square and this is 2y into derivative of y, that is y dash is equal to derivative of c is equal to 0. See, we can rewrite this as x plus y dash is equal to 0. We take 2 is out and this is equal to x plus y dash can again rewrite as x plus y dy by dx is equal to 0. I am taking this dx to be here, therefore, we can rewrite this as x dx plus y dy is equal to 0. This is a differential equation. The last is a differential equation which is derived directly from the function x square plus y square is equal to c square. Actually, x square plus y square equal to c square is a solution of the differential equation x dx plus y dy is equal to 0. Now, this differential equation x dx plus y dy equal to 0 is called a exact differential equation, But for the convenience, we develop the differential equation of this type, that is a differential equation, generally a differential equation of the form m of x y dx plus n of x y dy is equal to 0 is a differential equation. The differential equation of the form this type of differential equation is called exact differential equation if there exists a function u, that is a function in both x and y, is in implicit form, and this is a solution of this differential equation. I am taking it as a 1. This differential equation 1, u of x y is a solution of 1, and as well as we can write du is equal to m of x y dx plus n of x y dy. This is I am taking this as equation number 2. Now, say du is equal to m of x y dx plus n of x y dy. See, this is u is a solution of 1, then we can say that if there exists such a function u of x y, we can say that this is a exact differential equation. Equation number 1 is a exact differential equation. But actually, our aim is to categorize whether this type of differential equation 1 is exact or not. We are trying to derive a formula for to categorize whether our differential equation is exact or not. Generally, we have taken a differential equation of the type m of x y means a function in x and y. This is also n of x y means is an implicit function in both x and y, and this type of differential equation is exact. We are saying that there exists a function u of x y as a solution such that du is equal to m of x y dx plus n of x y dy. See, by the concept of total derivative, we can say that du is equal to dou u by dou x plus dou u by dou x into dx plus dou u by dou y into dy. I am taking this as equation number 3. See, first equation is m dx plus n dy equal to 0, second equation is du is equal to m dx plus n dy is equal to 0. The third equation, by the total derivative we can see that du is equal to dou u by dou x dx plus dou u by dou y dy is equal to 0. Compare 1, 2 and 3. If we are comparing these three equations, from here we can identify that m of x y is equal to dou u by dou x. M of x y is equal to dou u by dou x. Instead of m of x y, simply I am writing m for m of x y, and dou u by dou y is equal to n of x y. Therefore, dou u by dou y is equal to n of x y. Simply I am writing that as n. I am taking this as system as equation set 4. See, we can say that a type equation of the form m dx plus n dy equal to 0 is an exact differential equation if it's there exists a function u x y which is a solution of equation 1, and also if it satisfies the system 4, that is dou u by dou x equal to m, dou u by dou y is equal to n, is called a exact equation. To form again, I like to mention here dou m by dou y. I am writing dou m by dou y, sometimes my, and as well as dou n by dou x is there, sometimes I am writing for the convenience that as nx. See, I am differentiating this is, that is dou m by dou y. This is equal to dou m by dou y is equal to dou dou square u divided by, I am applying here it is dou m by dou y. Similarly, I have to apply dou by dou y is here. Therefore, while applying dou by dou y is here, we will have dou square u divided by dou y dou x. Similarly, I am applying here dou n by dou x, dou n by dou x, dou n by dou x. Dou n by dou x have to apply dou by dou x is here. Dou by dou x of dou u by dou y is equal to dou square u divided by dou x dou y. From here we can simply say that the differential equation 1 is exact if it satisfies dou m by dou y is equal to dou n by dou x. This is the necessary and sufficient condition for to say the equation 1 is exact. See, instead of this, sometimes we are writing, instead of dou m by dou y we are writing my, and as well as instead of dou n by dou x we are writing nx. So, sometimes we can simply say that if my is equal to nx, then we can say that our differential equation 1 is exact. So, while solving this type of differential equation, firstly we need to check whether the differential equation is exact or not. Firstly, we have to check whether our differential equation is exact or not. So, we are identified mxy as well as nxy. Then we will partially differentiate m with respect to y and partially differentiate n with respect to x. After that, if both the values are equal, then we can say that our differential equation is exact. If it is exact, we can solve that differential equation. Suppose sometimes maybe our differential equation is not exact. That means, if sometimes our differential equation my not is equal to nx, my not is equal to nx, then we can say that our differential equation 1 is not exact, So, if it is not exact, we are unable to solve that differential equation normally. First of all, we have to make a exact form of the differential equation, then we can solve. That we will discuss later. Here, first our aim is to solve the differential equation of the form m dx plus n ty equal to 0 if it is exact. See, I am giving some examples related to this. We can move to some questions. See example 1. Example 1, solve y cos x plus 2x e raised to y dx plus sin x plus sin x plus x square e raised to y minus 1 dy is equal to 0. See, this is of the form of m dx plus n dy. This is m of x y and this is n of x y. So, similarly we can write m is equal to y cos x plus 2x e raised to y, and n is equal to n is equal to sin x plus x square e raised to y minus 1. So, our aim is to check whether dou m by dou y is equal to dou n by dou x or not. We have to check this is if these two are equal, dou m by dou y is equal to dou n by dou x, we can say that our differential equation is exact. So, dou m by dou y, we are partially differentiating m with respect to y. That means x is treating as a constant. Now, cos x is a constant, derivative of y cos x is cos x, plus we are partially differentiating this with respect to y. So, 2x is a constant, therefore, e raised to y, we have to differentiate only e raised to y, derivative of e raised to y is e raised to y itself. Now, we are differentiating n with partially with respect to x. So, we are differentiating sin x, derivative of sin x is cos x, and plus here while differentiating partially with respect to x, we are treating the terms involving y are the constant. Here e raised to y is a constant. So, we have to differentiate only x square, derivative of x square is 2x e raised to y and derivative of minus 1 is 0. See, dou m by dou y is cos x 2x e raised to y as well as dou n by dou x is cos x 2x e raised to y, both are equal. Therefore, dou m by dou y is equal to dou n by dou x. Now, our differential equation, the given differential equation, I am treating that as equation number 1. Now, our differential equation 1, now our differential equation 1 is exact. Now, fine. Now, we are on the finest mode, we can solve this differential equation. How we will solve this differential equation? See, we know that we already discussed it is that there is a function u of x y is a solution. Let u of x y is solution of 1. We are supposing u of x y is a solution of 1. But because of this is exact equation, this that should satisfies dou u by dou x is equal to m and dou u by dou y is equal to n. So, take this as equation, set as a equation 2, system as equation number 2. See, we have dou u by dou x equal to dou u by dou x is equal to m. What about m? M is the y cos x plus 2x e raised to y. Therefore, this is equal to y cos x plus 2x e raised to y. We have to find u. To find u, integrating both sides. While integrating, we will have with respect to x integral of dou u by dou x, integral of dou u by dou x is equal to integral of y cos x plus 2x e raised to y dx. Therefore, this is plus some one more constant is there after integration. Now, our function, we know that our function u is a function in both x and y. We are differentiating only integrating only with respect to x. we are integrating only with respect to x. That is why integral of dou u by dou x plus integral of this quantity, the remaining is a constant that may be a function in y, maybe sometimes a fixed constant, maybe sometimes that may exist in terms of y, because we are treating y as a constant while partial differentiation. While integrating also we are we are treating y as a constant, that is why we are wrote here as h of y. So, integral of dou u by dou x, that is equal to u of x y is equal to integral of y cos x with respect to x, we are integrating with respect to x, y is a constant, derivative integral of constant, cos x is the integral of cos x is sin x, plus we are treating e raised to y as a constant, 2 as a constant. So, we are integrating only x, that is x square by 2 e raised to y plus h of y. So, u of x y is equal to y sin x, we can remove this 2 and 2 plus x square e raised to y, x square e raised to y plus h of y, x square e raised to y plus h of y. Say this is u, but actually one more unknown is here, the unknown is h of y, we have to find this h of y. For that we are again coming to the system 2. In system 2 we know that, dou n by dou y is equal to n. So, since dou u divided by dou y is equal to n, that is why we can say that dou u by dou y is equal to n, we have u is here. I am treating this as equation number 3, differentiate 3 partially with respect to y, differentiate 3 partially with respect to y, differentiate 3 partially with respect to y. See what will happen, instead of u it will come dou u by dou y, we are differentiating equation number 3 partially with respect to y. While differentiating a function partially with respect to y, we are treating x as a constant, or the functions involving x as a constant, all the terms which involved x we treat as a constant. So, here sin x is a constant, we are differentiating only y, therefore, derivative of y is 1, here it is sin x is there, and as well as here x square is a constant, we are differentiating only e raised to y, therefore, x square into derivative of e raised to y is again e raised to y, and derivative of h of y. Here h of y is a function of y alone, that is why even if you are differentiating with respect to y partially, that is like a ordinary derivative, therefore, we are just write that as a h dash of y. See from here dou u by dou y is equal to n. Since dou u by dou y is equal to n, we can write this is equal to sin x plus x square e raised to y plus h dash of y is equal to n. What about n? Sin x plus n is the sin x plus x square e raised to y minus 1. This is equal to sin x plus x square e raised to y minus 1. See, we have both sides have sin x and sin x is there, x square e raised to y and x square e raised to y is there. The remaining is h dash of y is equal to minus 1. H dash of y is equal to minus 1. Therefore, since h dash of y is equal to minus 1, our aim is to put value of h of y in equation 3. Therefore, we have just integrating, this is therefore integrating with respect to y, therefore, integral of h dash of y dy is equal to integral of minus 1 dy. Therefore, integral of h dash of y, integral of derivatives, again it will be the function, and this is equal to integral of minus 1 dy. Integral of minus 1 dy is y itself. Therefore, the solution we have got the solution is here. We already found the solution as equation 3. The equation 3 is u of x y is equal to y sin x plus x square e raised to y minus plus h of y plus h of y is there. Therefore, we are just replacing the value of h of y to be here. Therefore, this is equal to y sin x plus x square e raised to y plus h of y is there. The value of h of y we already found here, that is minus y, the minus y is here. See, this is the solution of the exact differential equation 1. Therefore, solution of 1 is, therefore, general solution of differential equation 1 is y sin x plus x square e raised to y minus y is equal to c is the general solution. As we discussed in the earlier sessions, this c is a arbitrary constant and it have an opportunity to take any value, it will be working as a variable. But if there exists, as like in all the previous sessions, we discussed the initial value problem. We already discussed the initial value problem or the differential equation with an initial condition. If they provide an initial condition, we can identify, we can find out a particular value for this c. On that case, in this case also, exact equation also, there exists a particular solution for the exact equation. Now, this is the general equation for our this equation, exact differential equation 1. Now, I am moving to the next one more example. Example 2. Y plus y cos of x y dx plus x cos of x y dy is equal to 0. This as we discussed earlier, this is stands for m. So, our equation is of the form m dx plus, and this stands for n, our equation is of the form n dy is equal to 0. We have to solve differential equation 1. To solve this differential equation, first of all we have to check whether our equation 1 is exact or not. For that, we need to find out whether dou m by dou y is equal to dou n by dou x, whether dou m by dou y is equal to dou n by dou x. See, we have m is here, m is equal to y plus y cos of x y. So, dou m by dou y, that is the my, is the derivative of y. Derivative of y is 1 plus derivative of y into cos x y. We have to use here, it is product rule. I am treating y as first function, cos x y as the second function. So, first function into derivative of second function, partial derivative of cos of x y, derivative of cos is negative of the sign, minus y sin of x y into derivative of x y. Since y is a variable, x is a constant, into x is there, plus second function cos of x y into derivative of y. We are partially differentiating with respect to y, therefore, derivative of y is equal to 1. Now, this is equal to 1 minus x into y, x y sin of x y plus cos of x y, sin of x y plus cos of x y. See, this is dou m by dou y. Now, we have to check what about dou n by dou x. So, we have n is here, n is equal to x plus x cos of x y, x cos of x y. Now, we are partially differentiating n with respect to x. While partially differentiating with respect to x, we are treating the terms of y as a constant. Partially differentiating x, derivative of x is 1, and as like the previous part, this is I am treating first function, this is I am treating as second function. We are using the product rule here. So, derivative of x into derivative of cos of x y. Derivative of cos is minus sine of x y, negative sign is here, and derivative of x y, x is a variable, y is a constant. Therefore, into y is here, plus for second function cos of x y into derivative of x. We are differentiating partially with respect to x, therefore, derivative of x is 1. Derivative of x is 1. See, this is equal to 1 minus x into y minus x y plus cos of x y. 1 minus x y into sine of x y plus cos of x y. See, this is dou m by dou x, this is dou n by dou x. Dou m by dou x equal to 1 minus x y sine of x y plus cos of x y. See, dou n by dou x is also 1 minus x y sine of x y plus cos of x y. So, what is the meaning? We found that dou m by dou y is equal to dou n by dou x. Now, our equation 1 is exact differential equation. Our equation 1 is exact differential equation, that is why we can solve the differential equation. So, we will suppose that there exists a function u of x y as a solution of 1, u of x y as a solution of 1, such that dou u by dou x is equal to m as well as dou u by dou y is equal to n. See, our m is here and as well as our n is here. So, I am taking dou u by dou x is equal to m. What about m? Y plus y cos of x y. Have to find u, integrating, we are integrating this with respect to x. Therefore, we will have integral of dou u by dou x, that is u of x y. Integral of y with respect to x, that is integral of y plus y cos of x y dx, plus constant of integration is there. We are partially we are integrating with respect to x. Our u is a function in both x and y. There are two variables, therefore, we are treating this constant as a function of y, h of y. This is equal to we are integrating with respect to x, y is a constant, integral of y x y plus this is y into y is a constant and cos of x y is there, integral of cos of x y sine of x y. Now, cos of a x, integral of cos of a x is sine of a x divided by a. Here we are integrating with respect to x, therefore, y is a constant, instead of a in denominator y will exist. Now, this is ok, plus h of y is here. Say this is x y plus we can cancel y and y, sine of x y plus h of y is here, this is u, I am taking this as equation 2, see equation 2. Now, equation 2 is a solution, u is actually u of x y. Now, we need to find out h of y. We are using to find h of y, we are using the second concept, that is dou n by dou u divided by dou y is equal to n. That is, I am differentiating partially to with respect to differentiate to partially with respect to y. So, what will happen? This is instead of u, there is a dou u by dou y will exist. Instead of x y, partially we are differentiating with respect to y, therefore, x is a constant, y is a variable, the x only remains there, and derivative of sine of x y, derivative of sine of x y is cos of x y, cos of x y, and one more thing is that x y cos a sine of a x is cos a x into a. So, here we are differentiating with respect to y, therefore, x is a constant, one more x will come there, and derivative of h of y, that is ordinary derivative h dash of y. See, dou u by dou x is equal to n. What about the value of n? N is x plus x cos of x y. See both sides, here x is here, and we can cancel this x and x will go on, and x cos of x y is there, here one x cos of x y, here also one x cos of x y is there. So, we found that is here. So, here it remains only h dash of y, that h dash of y is equal to 0, means since h dash of y is equal to 0 means h is a constant function. This implies h of y is equal to c. So, we can put in 2. So, our solution is u of x y is equal to x y plus sine of x y plus h of y means c. Therefore, the general solution is, as we did earlier, we have got u of x y. Therefore, general solution is only the variable part involves only x y, and sine of x y is there, and one more plus c is there. So, the general solution is x y plus sine of x y is equal to c is the general solution. As I discussed earlier, here there is not mentioned any of the initial condition, therefore, we are unable to find out a particular solution. This is a general solution. The same thing we can apply, we can use for a initial value problem if there exists a initial condition. There are many method, one more method to solve the exact differential equation that we will discuss on the next session. Thank you for watching this video. Continue the watching. Thank you very much.